Hello. In this video, we study the second fundamental theorem of calculus. As we discussed in the previous videos about the difference between definite integrals and indefinite integrals, we know that definite integrals are numbers, while indefinite integrals are families of functions, right? So we also discussed about the array functions, right, in the previous video. Look at this. So if your function f of x, suppose that that is non-negative function, right? So that's how we used to use definite integrals to find area of some region enclosed by the graph of the function on some interval a and b. So in this situation, the integral from a to b, that is just the area of this region, right? So you have a and b, you fix a and b, and you have that area. Now, if we consider the case when you just, you don't have b in here in the integration limits, right? So you just replace b with the x, where x is some point between a and b. So each time you may define, the area of this region. Does that make sense? And so, that is the area function. That's how we can define, the function f of x. Right? In this case, definite integral is a function depending on x. And of course, fb should be equal to the area of the region, right? On the whole interval. Agree? So this is another point of view on the definite integral. And since this is a function, we are interested in differentiability of such function, continuity of such function. Does that make sense? And it's obvious that the function is continuous, right? The function is continuous. But how about differentiability? So that is the main purpose of today's video. But before that, let's discuss some examples, okay? Let's evaluate the function f of x equal to 0 to x cosine t dt at x equal to 0 and pi over 6, for example. So, what is f0? You just plug 0 into the function, right? You get 0 to 0, cosine t dt, and of course that is 0. Second one, f of pi over 6. So basically you need to plug pi over 6, right, into the integral. You get cosine t dt, and antiderivative of cosine, I'm sorry, here should be pi over 6. Antiderivative of cosine is sine t, right? So you had evaluated from 0 to pi over 6. That is sine pi over 6 minus sine 0. Sine 0 is 0. Sine pi over 6 is, I guess that is 1 over 2. So the function value at pi over 6 is 1 over 2. So basically, if they give you a number, right, you just plug number into the formula of this function, and you evaluate that integral, you get what you need. Agree? So from point of view of geometry, you have the following picture. You have cosine, right? What is the graph of cosine? This is y, this is x, this is 1, this is negative 1. The graph of cosine from 0 to pi over 6. Okay, let's say here's pi over 2, right? Pi over 2. So pi over 6 is around here. Okay, this pi over 6. So the graph of cosine look like this on 0 to pi over 2, and this is pi over 6. So the integral is nothing but the area of this region. You see? So that's why, sometimes such functions are called area functions, okay? We might solve this problem in a different way. Look at this. So we evaluate the definite integral first, and then we plug 0 and pi over 6 into the answer. Okay, look at this. So your integral looks like from 0 2x, right? Cos of t dt. And that is sub t evaluated from 0 to x. So you get sub x minus sub 0. And we know sub 0 is 0. So basically that is sub x. So that means your function is nothing but, the sub x. Okay, let me rewrite it. Fx 0 to x cosine t dt equal to sub x. What can you see on this formula? You can see that derivative of x equal to cosine x. You see? Cosine. The integrand function is cosine t, right? But the integration limit is x. So you differentiate the function, you get cosine evaluated at x. So that gives you some idea about how to differentiate such function. Does that make sense? And that is about the second fundamental theorem of calculus. We suppose that the function f is continuous on some open interval I containing a. Okay, this is open interval. Then, for every x in I, the derivative of this function just equal to f evaluated at x. Okay, so what happens if you don't have x over there but a function? So we need to use the chain rule. For example, if you have integral from a to u of x, right, ft dt, and you want to differentiate this, so that is f of ux evaluated, f evaluated at u and then times u prime. See, that is the chain rule. Okay, so you see it is pretty nice, right? Pretty nice. Let's consider the following example. Let's find derivative of the function from 0 to the x, square root of t squared plus 1 dt, right? So I will differentiate this. I get, that's just the function, the integrand function evaluated at the x. You're done. You see? Now let's use the chain rule to find derivative of the following function. Integral from power 2 to x cubed cosine t dt. Of course, you can use the second fundamental theorem of calculus to do that. So, the derivative of x is equal to cosine evaluated at x cubed multiplied by x cubed derivative, and that is 3x squared cosine of x cubed, right? Or you may solve this integral. You have f of x is equal to sine of t evaluated from power 2 to x cubed, right? And you have sine of x cubed minus sine of power 2. Then you differentiate that. You get 3x squared cosine of x cubed, and the derivative of sine power 2 is just 0. So you get exactly like this. Does that make sense? Now let's go back to the very first formula when we consider the function f of x equal to integral from a to the x, f small t dt. And we just figured out from the second fundamental theorem of calculus, f derivative of x is equal to f of x. That means the capital function fx is an antiderivative of the function fx. Is that correct? So from here I can write f is an antiderivative. Okay, so again, right, we know from the first fundamental theorem of calculus, if fx is an antiderivative of f of x, then from here we know that integral from a to b f of x dx is equal to f of b minus f of a. Does that make sense? And of course, that is obvious from here. Y, in this case, f of a is equal to integral from a to a, ft dt. And that is just 0. You see that? And now you might plug this into this formula. You get the following. Integral from a to b f derivative x dx equal to fb minus fa. And this is called the net change. Okay, or the total change of the function f capital. On the interval a and b. That is about the net change theorem. Now, let's discuss the net change theorem from the point of view of the area problem. We talk a lot about the area problem, and each time when we solve that problem, we always need to make sure about the graph of the function. Do you remember that? So we might have the following picture, right? If the function is non-negative, so you always have this position, then the area is just definite integral from a to b of fx dx, right? Or that is f of b minus f of a, right? But in case your function looks like this, right? And let's say this is your a, this is b. So you can see that actually we have two regions in here. Does that make sense? So in order to find the area of this, I need to take integral from a to b of absolute of the function. Or in this case, I need to break the integral into two integrals if we have one intercept c in between a and b. So that should be equal to integral from a to c fx dx minus integral from c to b fx dx. We have minus in here because on b and c f of x is less than 0. You see this? So you have negative area. But in order to find the area, the actual area, you need to you cannot just take the negative, right? You have to subtract by the negative because you have absolute in here. Does that make sense? In general, if you have a function f capital and this function is differentiable, so this is the net change. I don't care about if the derivative is negative or positive on a and b, right? So this is the net change according to the net change theorem. And if you care about where the function is negative and positive, and you calculate the function value in here, but with the absolute dx, so this is called the total net change. I just picked this name because in the textbook they consider movement of particle, right? And they say that is total distance traveled or displacement, right? So the net change sometimes called the displacement, right? Displacement. That is also understandable because you just see the difference between the function value at b and a. So you just care the difference between them. Does that make sense? So this is some fa, this is some fb. That's it. But if you care about the total net change, so you need to consider the case of absolute, because like this, right? Because for this picture, if you just find the integral from a to b f of x dx, so you see you lost some area because you have negative area in this case. Does that make sense? So you just care about the change. You don't care about the total change. Does that make sense? So I hope you understand the difference between these two cases. the velocity of a particle moving along a line is Vt equal to t cubed minus 10t squared plus 29t minus 20, where the velocity is in feet per second and t is in second. Okay, the first question is, what is the displacement of the particle on the time interval 1 5? So they ask about the displacement, right? Means the net change. Does that make sense? So in this situation, you just need to find integral from where to where. Integral from 1 to 5 of the function Vt dt. And in the second question, they ask you, what is the total distance traveled by the particle on the time interval 1 5? So in order to find the total traveled, so you need to find the total displacement. That means you have to find the integral from 1 to 5 Vt absolute dt. Sometimes they are equal. If your function Vt is non-negative on that interval, but if your Vt change the sign on that interval, so they may not be equal. Does that make sense? So like we're discussing here in this picture. Okay. So let's solve this problem. That means we just need to evaluate two integrals. So for the first question, I need to find integral from 1 to 5. Vt is t cubed minus 10t squared plus 29t minus 20 dt. And antiderivative of t cubed is t to the fourth over 4 minus 10 t cubed over 3. And antiderivative of t is t squared over 2 minus 20t. And this is evaluated from 1 to 5. So our job is just plug 1 and 5 into this function. Okay. I hope you can do that yourself. So the answer is 32 over 3. So that is the net change, or that is the displacement of the particle on that time interval. Okay. And for the total net change, or for the total distance traveled, so we need to integrate the absolute of v. So we have absolute of t cubed minus 10t squared plus 29t minus 20 dt. So it is a little bit complicated, because you need to see when the function is positive, when the function is negative. In order to do that, you need to find all zeros of the function. Does that make sense? Because you have to remove the absolute. So I have to solve t cubed minus 10t squared plus 29t minus 20 equal to 0 to find all zeros of this polynomial. So we know, right, from precalculus that how to guess zeros of a polynomial like this. So basically, you may find, that is the coefficient of t cubed is just 1, right? Here you have negative 20. So you need to consider all possible, like negative 20, let's say plus minus 20 over 1, and so on, plus minus 10 over 1. Actually, yeah, just 1, right? Just 10, right? And then plus minus 4, plus minus 5, plus minus 2, and then plus minus 1. Okay, so we may try, you plug all these numbers right into this polynomial and see which one is 0. But in this case, our polynomial is very special. Look at this. You take sum of all coefficients, you get 0. Right? So sum of all coefficients in here is just 1 minus 10 plus 29 minus 20 equal to 0. Then from here, I can tell you, we can do conclusion that t equal to 1 is a 0. It's obvious, right? Because, if t equal to 1 is a 0, you just plug 1 into the polynomial, right? So you get sum of all coefficients. Does that make sense? So I have 1, 0. I can factor. Then I can factor the polynomial by t minus 1. I have t cubed minus 10t squared plus 29t minus 20 equal to t minus 1. Okay, you might do long division, but in this case I don't have to do that. Okay, now I start from t, right? Here we have t cubed. That means here we would have t squared, and then I multiply t squared back here. I don't need to multiply with the t because I know exactly, right? That is should be t cubed. So I multiply t squared with negative 1. I get negative t squared. But here we have negative 10t squared. That means here we need negative 9t. Why? Because if you have negative 9t in here, right, you multiply with this t, you get negative 9t squared. Together with negative 1t squared in here, you get negative 10t squared. Does that make sense? And then you finish with t squared with 9t, so the last one should be the free coefficient, right? The free coefficient in the original is negative 20. You have negative 1 in here, means here you should have plus 20. That's how I can divide. I can factor, okay? So that's good. And then you set this equal to 0. From here you get t equal to 1 or t squared minus 9t plus 20 equal to 0. You have quadratic polynomial. You might use quadratic formula, okay? And you need to check b squared minus 4ac. In this case, you have 9 squared minus 4 times 20, right? So that is 81 minus 80 equal to 1, bigger than 0. That's good. The polynomial has 2 zeros, right? I mean, this equation has 2 zeros. So you have t1, 2 is equal to negative b plus minus square root of b squared minus 4ac over 2a. So that is the formula. Now you plug negative b is 9 plus minus 1. We just calculate b squared minus 4ac, right? Just square root of 1, which is 1. A is just 1. So from here, I will get 5 or 4. Look at this. So basically, our polynomial t cubed minus 10t squared plus 29t minus 20 equal to t minus 1 times t minus 4 times t minus 5. Okay? And now we need to consider the sign of this polynomial on those intervals. And we do this a lot when we study the first derivative, right? So we need to make the chart. In the first row, we have t. In the second row, we have the function, right? Because we want to see the function, the sign of the function. So the function is from negative infinity to positive infinity. But in this case, yeah, look at this. We are considering the case, the integral from 1 to 5. And all these 3 points are in 1 to 5. So you don't need to consider negative infinity to positive infinity. Sorry for that. You only need to consider, 1 and 5, okay? 1 and 5 in here, and in here you have 4. So the function value is 0, 0 in here, 0 in here. You have 2 intervals, right? You might pick 2, okay, and you plug 2 into the function. You plug 2 into the function, you get this term is positive, this term is negative, this term is negative. So the product would be positive. You see, positive, negative, negative. So positive, right? You might pick 4.5 in here. Now the first term is positive, the second term is positive, but the last term is negative. So the function is negative on this interval. Then your integral may be rewritten in the following form. 1/5 absolute of t cubed minus 10t squared plus 29t minus 20 absolute dt equal to integral from 1 to 4, and the function is positive, so we can write just t cubed minus 10t squared plus 29t minus 20, right? Because absolute is just equal to that function, right? Because we have positive in here. And then minus integral from 4 to 5 t cubed minus 10t squared plus 29t minus 20 dt. Does that make sense? And now you just need to evaluate, antiderivative. But I think we already did that in the previous question. So you have function right here, right? So basically you just need to apply the function on 0, 4 and 4, 5, and you get what you need. Okay, anyway, let's write it down and then we finish this example. So you have t to the 4 over 4 minus 10 t cubed over 3 plus 29 t squared over 2 minus 20t. Okay, evaluated from 1 to 4 and then minus, I just copy this again, t to the 4 over 4 minus 10 t cubed over 3 plus 29 t squared over 2 minus 20t, evaluated from 4 to 5. And then you plug all these numbers into the function, you get 45 over 4 minus negative 7 over 12. And that is 71 over 6. Does that make sense? So basically, you can see, yeah, in this case, the language is difficult, but if we look at this from the point of view of the area problem and the net change theorem, it says, yeah, in order to find the displacement, you just need to evaluate the definite integral. But in order to find the total distance traveled or the total displacement, you need to evaluate the area, right, of the region enclosed by the graph of that function on the given interval. Does that make sense? So I think I finished my video in here. Okay, so we are done with the first and the second fundamental theorem of calculus, right? In the last section we'll study integration by substitution, and that's how we can finish this chapter. Thank you and see you.